All right, so when a nitrogen nucleophile, like one in an amine, adds to a carbonyl, something a little different happens depending on what type of amine it is. Okay? This one over here, RNH2, is a primary amine. R2NH is a secondary amine. Okay? Just looking directly at how many R groups are attached. Primary amines will add to carbonyls. The C double bond O will be replaced by a C double bond N, and both of those H's will go away from that N. So that is an imine. If I have a secondary amine, both of the R groups will remain on the N, but we can't have a C double bond N then, right? Because nitrogen would be exceeding its valence. So what happens is we actually eliminate an H adjacent to the carbonyl carbon and make a CC double bond. So we get CC double bond with NR2 next to it. That is an ene amine. So even though these two products look fairly different, the mechanism for their formation is actually identical except for the very last step. So let's draw a simple mechanism here. Let's just start with acetone. The book goes ahead and has the neutral nucleophile add to the carbonyl right there. I actually like a little better the mechanism where, like we said, if something is acid catalyzed, like this one is, it's doesn't have to be in the presence of a strong acid. We'll talk about the pH range, but still it makes a more consistent rule, and the mechanism is really just as correct. So what I like doing is having the carbonyl oxygen be protonated first. I'm just going to say H+. I'm not going to say hydronium anymore. I guess you could. It's not a huge deal, but let's protonate carbonyl. If it helps you to draw the resonance structure with the C+, that's great. That's up to you, but it's not necessary. I'm going to start with a primary amine. Let's just do methylamine, CH3NH2. The neutral nucleophile is able to add to the carbonyl now because the carbonyl has been activated towards addition. So I think that makes a nice structure. So we have the OH from what used to be the carbonyl. We now have N with two H's and a CH3 attached. This is a nitrogen with 4 bonds, so it has to be plus charged. A good way of keeping track of your charges, and that's probably the most important thing in doing a mechanism like this, is to keep very careful track of your charges. In the preceding structure, we had a single plus charge between all these. And in the adduct, in the thing that was formed from them, I have a single plus charge. So those charges will always be conserved from one step to the next. And the only way to get rid of charges is if you're getting rid of a plus and a minus, for instance. Okay? So what's going to happen, water or some other base that's around will remove one of these hydrogens. I'm drawing equilibrium arrows because this, like all these other things, is reversible. Like all these acid-catalyzed carbonyl reactions, completely reversible. So I'm drawing reversible equilibrium arrows between all of the structures. One sort of general rule that we've talked about in class before is that you can only have one plus charge in the molecule at a time. If we think ahead a little bit into the future, this alcohol has to be protonated so it can leave, but I can't do that until I get rid of the N+. Right? So to get rid of an N+, we take it back down to 3 bonds by removing one of the hydrogens. So HO, N, CH3, H. Nitrogen now has a lone pair, is neutral. We've regenerated an acid catalyst, which I can draw as hydronium now. That's fine. So I can protonate the alcohol. I can call this NHCH3, abbreviate just a little bit. I can call that H2O plus. Okay. Nitrogen's lone pairs. Same thing now is going to happen that's happened an awful lot. Nitrogen's lone pairs will come down, causing the water to be ejected. Leaving us with a nitrogen double bond, NH, CH3. Right, like that. I've also formed a molecule of water, which will remove that hydrogen, giving us our product, an imine. Okay. So that imine came from our primary amine. Draw a box around that. Okay. Now, if instead of this primary amine, I had a secondary amine, like dimethylamine, CH3NH, all of this stuff will be the same, except instead of this H on the CH3, I have another CH3 group, right? Let me do a little different color here. It's all the whole mechanism will be the same right to this point, right here. And if a secondary amine is used. Okay. This was after the nitrogen donated its electrons in to kick the water out. Okay. Before, when we had an H on that end, we just deprotonated. Okay. We got our neutral imine, and we were in good shape. Now, no H on that nitrogen. The only thing we can do to get rid of that plus charge is to get rid of the double bond. And to do that, we have to find a way to donate those electrons in, so I'm going to make a double bond here. Okay, so let's take water, attack one of the hydrogens on the carbon next to the double bond. Okay, that forms a new CC double bond. That kicks the Cn electrons back up onto nitrogen, which will remove its positive charge. We will now have this compound, NCN single bond, CH3, going off in both directions. This is an ene amine. That we get by, instead of using a primary amine, use a secondary amine. Right? Right here, the difference is right in here. That came from that structure. So you can get to this point in the mechanism by doing everything identical to what happened there. I mentioned acidic, right? This has to be done under acidic solutions, right? pH 4 to 5 is best. It makes the reaction go fast enough. So let's think about why that is. If we had a higher pH, okay, if our solution was neutral or basic, we would not protonate the carbonyl, like we need to do to get the OH in the very first step. If it was more acidic than 4 or 5, we would protonate the nitrogen right there. Okay. right? We have RNH3 plus, which is no longer a nucleophile at all. So 4 to 5 is the sweet spot where we can still have a nucleophilic nitrogen, but also still have an electrophilic carbonyl. Oh, for practice on this, you should start with the imine and the enamine and go backwards, right? I'll give you a hint. What'll happen to get from here to here is the lone pair will come down. This will attack NH to get protonated, right? Then what? Water attacks this. Get something like that. Deprotonate the water, right? Protonate the nitrogen. This can kick off that as a leaving group and so on. So just for fun, just for practice, on a blank piece of paper, make sure you can draw the mechanism for formation of either of these. Okay? Going in the forward direction, then try it in the reverse direction, since these are indeed reversible reactions. So why on earth would we want to form one of these nitrogen compounds, an imine, right, or an enamine? A lot of it is kind of old chemistry, towards the beginning of this century. It's not nearly as modern, but it's still very useful in that if I have a product that's a ketone or an aldehyde, most of them are liquids, and there are no cheap, easy ways of definitively characterizing a liquid compound, right? This was before IR and NMR and things like that. So if I made a solid product, we can recrystallize it to purify it very easily. Then we can take a melting point. We've done that a million times in lab already. So to make a liquid product into a crystalline solid, which can be recrystallized, purified, and had a melting point measured, we can make an imine out of it. It's called a derivative. So if I, for instance, use hydroxylamine, we can make a product called an oxime, right, which has a C double bond N OH on that. And these oximes can have specific melting points depending on what carbonyl compound made them. So there are reference tables that list off melting points of hundreds of different ketones. So one way is if you have an unknown ketone, make one of these derivatives of it, measure its melting point. Maybe make a different derivative, measure that melting point, and you'll be able to narrow down your product pretty easily. So that was making an oxime. We make a 2,4-dinitrophenylhydrazone. Right? That's this compound. That's a hydrazone, is a C double bond N with an N next to it. So you may recognize this because dinitrophenylhydrazone is abbreviated DNPH. So if you took 1062 at our school anyway, we have an experiment where we can identify a ketone by reacting it with 2,4-dinitrophenylhydrazine. That makes this crystalline solid product, which can be a positive test for a carbonyl. So alcohols and other things, just alkenes, hydrocarbons like that will make no solid product. But if I have a carbonyl, reacting it with the NPH will make a really nice white crystalline precipitate. That's actually useful, though, more than just a test for a carbonyl. If we recrystallize that product, measure its melting point, we can use it to figure out our compound. In fact, recrystallizing used to be the only main way that compounds were purified before column chromatography and things like that. So if you have a liquid product, you make some sort of derivative out of it, recrystallize it, and then reform the carbonyl compound, which will be much more pure.